Welcome to the Hypnos Sleep Channel. Tonight, Hypnos, the ancient Greek god of sleep, will guide us on an extraordinary journey through the science of gravity. Not only the force that keeps your feet on the ground, but one of the deepest organizing principles in the universe. We are going to explore not only why things fall, but why planets form, why moons circle worlds, why light can bend, why clocks can disagree, and why the largest structures in existence gather into filaments, clusters, and galaxies. Gravity is the most familiar force in daily life, and still one of the least fully understood. You meet it every time you stand, lift a cup, climb a stair, or watch rain fall from a cloud. And yet, the same invisible rule reaches outward to shape the motion of oceans, the birth of stars, the curve of spacetime, and the unfinished questions at the edge of modern physics. So, tonight we begin close to home, with a feeling so ordinary that it almost disappears. The quiet fact that Earth is holding you. You are standing on the surface of a planet, though most of the time it does not feel that way. It feels like a floor beneath your feet, a chair beneath your body, a street, a room, a patch of ground. But beneath that ordinary contact is an entire world: rock, metal, ocean, atmosphere, and deep interior mass, all gathered into a sphere more than 12,000 kilometers wide. The feeling you call weight begins there, with Earth pulling on you from every part of itself at once. What are you actually feeling when you feel weight? It is tempting to say you are feeling gravity directly, as if gravity were a pressure pressing down on your shoulders. But the more precise answer is slightly stranger. Gravity is pulling you and everything around you toward Earth's center. The floor prevents you from continuing downward. So the sensation in your feet, legs, spine, and muscles is not only the pull itself, it is the support force from the ground pushing back against you. If the floor suddenly disappeared, that feeling would change immediately. You would still be under Earth's gravity, but for a brief moment you would not feel the same weight. You would be in free fall, moving with the pull instead of being held against it. This is why a falling elevator, a diving aircraft, or an astronaut in orbit can feel weightless while gravity is still present. Weight is not simply the existence of gravity. It is the experience of being supported while gravity tries to accelerate you. This corrects one of the quiet misunderstandings built into everyday language. Your mass and your weight are not the same thing. Your mass is your resistance to acceleration, the amount of matter and energy that gives your body inertia. It travels with you. Your weight depends on the gravitational field you are in and on how strongly something is supporting you against that field. On the moon, you would have the same mass, but you would weigh much less because the moon's surface gravity is weaker than Earth's. Imagine holding a heavy suitcase here on Earth. Your arm works because the suitcase has mass, and Earth's gravity gives that mass weight. Now imagine carrying the same suitcase on the moon. The suitcase has not lost most of its material. The atoms are still there. Its inertia is still there. If you tried to swing it quickly, it would still resist the motion. But lifting it would feel easier because the moon pulls it downward with less force. The object is the same object. The local gravity has changed the demand it places on your body. From where you stand now, Earth dominates the scene so completely that it is easy to forget gravity belongs to everything with mass energy. The walls, the furniture, a nearby mountain, your own body, and even a cup on a table all participate in gravity. They all pull extremely slightly on everything else, but their masses are small compared with the planet beneath you. Earth is not the only object exerting gravity. It is simply the overwhelming one in your immediate life. Here is the surprising part. The entire planet is involved in the feeling at the bottom of your feet. Not just the ground directly below the room, and not just the rocks nearest you. Every piece of Earth contributes to the gravitational field you are standing in. The deep mantle matters. The iron-rich core matters. The oceans and mountains matter a little too. Gravity is cumulative, and Earth's mass is gathered close enough beneath you that its total effect becomes the most familiar force in your life. If you could see gravity the way you see light, the room would not look empty. There would be a direction built into the space around you, a quiet tendency toward Earth's center. Loose objects would reveal it whenever they slipped from a hand or rolled from a table. A dropped key does not choose the floor. It follows the acceleration produced by Earth's gravitational field until the floor interrupts that motion and turns falling into impact. The same is true of your own body, only more gently and continuously. Your bones and muscles are always negotiating with the planet. Your skeleton is a structure built under gravity's instructions. Your balance system has learned which way down is because Earth has supplied that direction since before you had words for it. Even standing still is not an absence of motion in a deeper physical sense. It is a continuous exchange, Earth pulling, the ground supporting, your body arranging itself between the two. And yet gravity does not feel dramatic here. That is part of its power. It is steady enough to vanish into the background of consciousness. You notice it when you lift something heavy, climb a hill, trip, jump, or watch rain fall from a cloud. But in the ordinary quiet of standing, gravity becomes almost invisible, even while it defines the shape of every moment. It gives the room an up and a down. It gives oceans their resting surfaces. It gives the atmosphere a reason to remain wrapped around the world. From this first viewpoint, gravity is not yet a galaxy, a black hole, a wave in space-time, or a mystery at the edge of physics. It is the simple fact that the planet is pulling you inward and the surface is answering by holding you up. The feeling is familiar enough to ignore, but the science inside it is already profound. Your weight is a local conversation between your body and Earth, between mass and support, between falling and being stopped from falling. And once that is clear, the next question becomes unavoidable. If gravity can feel so ordinary under your feet, how can it also build planets, guide moons, bend light, and gather galaxies? To understand that, we have to look at a strange imbalance. Gravity is the weakest of the familiar forces, and yet on the largest scales, it becomes the architect of almost everything. Imagine a small magnet resting on a table. Beneath that table is Earth, a planet with a mass of about 6 trillion kilograms, pulling everything downward. And yet, if the magnet is brought near a paperclip, the little piece of metal can leap upward against the pull of the entire world. From this close range, electromagnetism wins easily. The paperclip rises and the planet loses a tiny contest you can see with your own eyes. What does that tell us about gravity? The answer is not that gravity is unimportant. It tells us that gravity is astonishingly weak between ordinary objects. A magnet the size of a coin can overcome Earth's pull on a paperclip because electromagnetic forces between atoms and charges are far stronger at human scales. Gravity is always present, but in the room around you, it is usually too faint between small objects to notice. The number that describes gravity's strength in Newton's equation is called the gravitational constant, written as G. It is a very small number in everyday units, approximately 6.67430 times 10 to the negative 11th. That value is not a magical explanation of why gravity is weak at the deepest level, but it does tell physicists how weak the measured force is between laboratory-sized masses. If two books sit beside each other on a shelf, they attract each other gravitationally, but the pull is so tiny that friction, air currents, and the stiffness of the shelf overwhelm it completely. Here is the surprising part. Gravity is weak, but it is cumulative. Electric charge comes in positive and negative forms, so large objects are usually almost neutral overall. The electrical pushes and pulls mostly cancel out. Gravity does not cancel in that ordinary way because mass energy contributes with the same sign. A mountain, a planet, a star, and a galaxy can keep adding their influence until the smallest force becomes the one that organizes the largest structures. If you were floating far from planets, a single pebble would not draw you in with any obvious urgency. But gather enough pebbles, enough dust, enough ice, enough rock, and the story changes. A world begins as many small pieces, each contributing a little. The pull remains weak between any two grains, yet over time the combined mass can become large enough to round itself into a planet, hold an atmosphere, and carve moons into orbit. This is why gravity is so different from a force that shouts. It does not need to dominate at the scale of a paperclip. It waits for numbers, distance, and accumulation. On the scale of your desk, it is almost hidden. On the scale of Earth, it becomes the direction called down. On the scale of the sun, it holds planets in long, repeating paths. On the scale of a galaxy, it becomes a deep architecture of stars, gas, dust, and dark matter. If you could make every force visible in the room, gravity might look almost shy at first. The chemical bonds in the table, the electrical repulsion that keeps your hand from passing through the surface, and the magnetic tug on the paperclip would seem far more assertive. But then the view would widen. The walls would become part of a city, the city part of a planet, the planet part of a solar system, and gravity would begin to show its advantage. It is not easily blocked. It keeps adding. It crosses empty space and gathers the quiet sum of mass. Consider the ground beneath you again. The floor is not strong because gravity is strong between the floorboards and your body. The floor supports you because matter is held rigid by electromagnetic forces inside atoms and molecules. Gravity pulls you downward, but the solid surface resists compression through electrical interactions in matter. Your everyday experience of weight is therefore a meeting between two forces, gravity providing the downward acceleration and electromagnetism in the floor refusing to let your atoms pass through its atoms. This is one reason gravity feels so mysterious. It is the most familiar force in your life, and yet in a direct contest between small objects, it is almost always the weakest. You can lift your hand against the pull of Earth. A refrigerator magnet can cling to metal. Static electricity can make hair rise. But given enough matter, gravity becomes patient and unavoidable, collecting worlds, shaping stars, and drawing the universe into structure. So the question becomes sharper. If gravity is weak, how does it decide how much to pull? Why does the moon influence the oceans, while a nearby building hardly matters? Why does distance soften gravity so quickly? And why does mass make it stronger? To answer that, we move from the feeling of weight to a quiet rule, one simple enough to write in a line and powerful enough to send spacecraft between planets. Imagine pulling far away from Earth until the planet becomes a blue sphere and the moon becomes a smaller gray companion. From this distance, the space between them becomes visible. The moon is not close in the way a cloud is close. It is hundreds of thousands of kilometers away, circling Earth across a gap wide enough to fit many Earths between them. And still, the two worlds are connected by gravity. How does that connection know its strength? In Newton's description, the answer depends on two things: mass and distance. More mass means more gravitational pull. More distance means less pull. But distance does not weaken gravity in a simple one-for-one way. It follows an inverse square rule. If you move twice as far away, the pull becomes 1/4 as strong. If you move 3 times farther away, it becomes 1/9 as strong. This is not just a mathematical detail. It is the reason gravity can be both local and cosmic. The moon can raise tides because it is close enough for its pull to vary across Earth. The sun is far more massive than the moon, but it is also much farther away, so its tide-raising effect is smaller than the moon's. Distance matters so strongly that closeness can compete with size. If you could draw invisible shells around Earth, each shell twice as far out as the last, the same gravitational influence would be spread over more area as it travels outward. The geometry of space dilutes the pull. A light bulb gives a similar lesson. Close to the bulb, light is intense. Farther away, the same light is spread across a larger sphere, so the brightness drops rapidly. Gravity is not light, but the same geometry of spreading helps explain why inverse square laws appear in nature. Newton's law is also a reminder that science can be profoundly useful even when it is not the final word. General relativity gives the deeper description of gravity as space-time curvature, but Newton's equation still works extremely well for most everyday and astronomical situations. It can guide spacecraft, explain falling objects, describe planetary orbits to high accuracy, and let engineers plan trajectories through the solar system. It is an approximation, but a brilliant one. From a human viewpoint, the inverse square rule also explains why distance can be more important than instinct suggests. A nearby mountain has mass, and it does pull on you slightly, but Earth surrounds you with vastly more mass. The moon is far away, yet large and close enough on planetary scales to matter for tides. The sun is enormous, yet so distant that its tide-raising effect is reduced. Gravity is not judged by size alone. It is judged by size through distance, and that relationship quietly decides which influences become important. From your distant view, Earth and the Moon are not merely pulling on each other. They are both moving around their shared center of mass. That point lies inside Earth because Earth is much heavier, but the Moon still makes the planet wobble slightly. This correction matters. Gravity is not only one object acting while another obeys. Every mass responds. The smaller motion may be harder to see, but the relationship is mutual. Here is the surprising correction. Gravity does not need contact, and it does not require a visible connector. The Moon does not hang from Earth by a rope. Earth does not drag it through space like a stone on a string. The old Newtonian language speaks of attraction across distance, while the later Einsteinian language speaks of motion through curved spacetime. Both descriptions, used carefully, tell us that the Moon's path is not random. It is shaped by mass, distance, and motion. If the Moon stopped moving sideways, it would fall toward Earth. If Earth had no gravity, the Moon would travel away in a straight line. The orbit exists because both facts are true at once. The Moon has forward motion, and gravity continuously bends that motion. This is the bridge from Newton's quiet rule to one of the most elegant ideas in physics. An orbit is not a place where falling stops. It is falling that never quite reaches the ground. Imagine you are inside a spacecraft above Earth. A notebook floats beside you. A drop of water releases from a pouch and hangs as a shimmering sphere. Your body does not press into the floor in the ordinary way. From inside the cabin, it feels as if gravity has been turned down almost to nothing. But outside the window, Earth fills half the view, vast and close, still pulling on every object in the spacecraft. So is there really no gravity in orbit? The answer is no. Low Earth orbit still has most of Earth's surface gravity. Astronauts do not float because they have escaped the planet's pull. They float because they, the spacecraft, the notebook, the water, and everything loose inside are all falling together along the same curved path around Earth. Without a floor pushing back differently on each object, the usual feeling of weight disappears. This is one of the most useful corrections in all of space science. Zero gravity is a common phrase, but near Earth it is not literally true. The International Space Station is not beyond Earth's influence. It is falling around the planet at high speed. Its sideways motion carries it forward while gravity bends its path downward. The surface curves away beneath it, so the station keeps missing the ground. Picture throwing a ball from a mountain. Toss it gently, and it lands nearby. Throw it faster, and it travels farther before touching the ground. If it could move fast enough, and if air resistance did not slow it, the ground would curve away as quickly as the ball fell. The ball would never stop falling, but it would also never hit Earth. That is the basic idea of orbit: forward speed plus inward acceleration. This thought experiment is old, but it remains powerful because it connects the ordinary to the orbital. A thrown ball, a cannonball, a satellite, and the Moon belong to the same family of motion. The differences are speed, altitude, resistance, and scale. The ball hits the ground because Earth is close and air slows it. The satellite misses because its sideways motion is large enough and its path begins above most of the atmosphere. The moon misses because it is already moving around Earth across a much larger path. The important detail is that speed and gravity do not cancel. Gravity is not switched off by motion. It provides the inward acceleration that bends the path. Without that inward pull, the spacecraft would move in a straight line and leave Earth behind. With too little sideways speed, it would descend. With the right speed, it continually falls around the planet, tracing a path that repeats. From the window, Earth is not simply below you in the ordinary sense. It is the curve your motion is wrapped around. The horizon bends in every direction, and your path is part of that curvature. If you release a tool inside the cabin, it does not drop to the floor because the floor, the tool, and your body share the same fall. Weightlessness is not the absence of gravity. It is the absence of support force. This brings us back to the feeling of standing on Earth. On the ground, the surface interrupts your fall. In orbit, the spacecraft is not interrupted in the same way. It falls with you. The difference between weight and weightlessness is therefore not just location. It is whether something is preventing you from following gravity freely. Here is the quiet beauty of the idea. A satellite is not hovering. It is not held up by some invisible platform. It is falling with exquisite precision. Its path is a compromise between straight-line motion and the planet's pull. The same physics that makes a dropped key hit the floor can, with enough sideways speed, carry a spacecraft around Earth for years. And once we understand that gravity is not only a downward pull but a shaper of motion, the moon becomes more than an object in the night sky. It becomes a partner in Earth's motion, pulling unevenly across the planet. That unevenness is small, but oceans are wide, and water can answer. To see gravity's reach in daily life, we only have to stand at the shore and watch the tide come in. Imagine standing at the edge of the sea while the water slowly climbs the shore. Nothing sudden is happening. The change is almost too gradual to notice from 1 minute to the next. But over hours, the boundary moves. Rocks that were dry become wet. Sand disappears beneath a thin, moving sheet. The ocean is answering a force that reaches across space from the moon. How can the moon move an ocean? The answer is not simply that the moon pulls upward on the water. The real cause of tides is the difference in gravitational pull across Earth. The side of Earth closer to the moon is pulled a little more strongly. The far side is pulled a little less strongly. That difference stretches Earth and its oceans along the Earth-Moon line, creating tidal bulges. This is called a tidal force, and it matters because gravity changes with distance. The moon's pull at Earth's near side is slightly stronger than its pull at Earth's center, and slightly stronger still than its pull on the far side. The differences are small compared with Earth's own gravity, but the oceans are enormous and mobile. Across planetary distances, small differences can reorganize water. The sun also raises tides. It is vastly more massive than the moon, but much farther away, so its tide-raising effect on Earth is smaller. When the sun, Earth, and moon are roughly aligned, the lunar and solar tidal effects combine into stronger spring tides. The name has nothing to do with the season. The water is springing higher and lower because of alignment, not because the calendar says spring. Local tides are more complicated than a clean diagram. Coastlines, seafloor shape, ocean basins, winds, and currents all affect the actual height and timing of water at a specific shore. A bay can amplify tides. A coastline can delay them. The moon supplies the broad gravitational pattern, but Earth translates that pattern through geography. The tide at your feet is both celestial and local. This is why two coastlines under the same moon can experience very different tides. One harbor may see water rise dramatically, while another shore changes more gently. The gravitational forcing is global, but the ocean is not a simple smooth shell. It sloshes in basins, reflects from continents, and resonates in ways shaped by depth and coastline. Gravity begins the pattern, but the planet's surface edits it into local timetables, currents, and shorelines. Here is the surprising part. Tides do not belong only to water. Solid Earth flexes too. The ground beneath you can rise and fall slightly under tidal forces, though the motion is not usually noticed in daily life. Other worlds feel this even more dramatically. Moons orbiting giant planets can be stretched and squeezed by tides, and that repeated flexing can heat their interiors. Gravity can warm a world without sunlight, simply by changing its shape again and again. If you watch the shoreline with this in mind, the scene becomes less ordinary. The water is not just moving because of waves or wind. It is part of a planetary response to a body in the sky. The moon is not lifting one puddle. It is stretching the whole Earth system, and the ocean reveals the distortion in a way the eye can follow. This also corrects a common picture. The moon does not drag a single mound of water around Earth like a hand pulling cloth. Tides are patterns produced by gravity, Earth's rotation, ocean dynamics, and basin shape. The bulge picture is a helpful beginning, but the real ocean is a moving, resonant, geographically shaped system. Science becomes more beautiful when the simple picture opens into the real one. At the shore, gravity feels slow and wide. It does not strike like lightning. It appears as a patient rearrangement of water under the geometry of Earth, Moon, and Sun. And this prepares us for a deeper change in the story. Newton gave us a rule for gravitational pull, but in the 20th century, gravity itself was reimagined. The question shifted from how strongly objects attract to what kind of shape mass gives to space and time. Imagine watching Earth travel around the Sun from far above the solar system. In a simple picture, the Sun pulls and Earth obeys. The planet is like a stone on an invisible string, forever tugged inward while its sideways motion carries it around. That picture works well enough for many calculations. But Einstein asked for something deeper. What if gravity is not merely a force acting through space? What if it is built into the shape of space and time themselves? General relativity reframed gravity. In this theory, mass and energy curve spacetime, and objects moving freely follow the straightest possible paths through that curved geometry. A planet orbiting a star is not being dragged along a hidden track. It is following a natural path in a space-time shaped by the sun. The path looks curved to us because the geometry it moves through is curved. This idea can sound abstract until we ask what a path means. On a flat map, the shortest route between 2 points looks like a straight line. On a globe, the shortest route follows a great circle, which may appear curved when drawn on a flat projection. Geometry changes what straight means. General relativity says that gravity changes the geometry of the universe itself, so free motion follows curves that are actually the straightest available routes in spacetime. The familiar rubber sheet analogy can help at first. Place a heavy ball on a stretched sheet, and the sheet dips. Smaller balls roll along curved paths. But the analogy has limits. It uses Earth's gravity to make the sheet sag, so it cannot fully explain gravity without borrowing gravity. It also shows mostly space, while real relativity includes time as well. The deeper lesson is not that space is a literal fabric, but that geometry is dynamic. If you could replace the rubber sheet with a map of possible paths, the lesson would become cleaner. Near a massive object, the routes that free objects naturally follow are no longer arranged as they would be in empty, flat spacetime. They lean, curve, and converge in ways determined by the mass energy present. A planet is not choosing to orbit. A falling object is not searching for the ground. They are following the available geometry, while forces such as the ground support push objects away from those free paths. Here is the surprising correction. In relativity, gravity is not a mysterious hand reaching out from one body to another. It is the effect of space-time telling matter how to move, while matter and energy tell space-time how to curve. That phrase is often paraphrased because it captures the relationship beautifully. The arena is not passive. The stage responds to what is on it. From this viewpoint, a falling object near Earth is not simply being pulled downward in the old sense. It is moving along a path through curved space-time. The ground interrupts that natural path, and the support force makes you feel weight. This connects Einstein back to your own body. Standing still on Earth is not the simplest state in relativity. Free fall is closer to natural motion. The surface is what prevents you from following it. This is why an astronaut in orbit feels weightless while still under gravity. The astronaut is following a free fall path through curved space-time. The person standing on Earth is being pushed upward by the ground, away from that free path. The idea reverses intuition. The person floating in orbit is, in a sense, moving more freely than the person standing still. General relativity also made testable predictions. It explained the small extra shift in Mercury's orbit that Newton's theory could not fully account for. It predicted that light would bend near massive objects. It predicted that clocks would run at different rates in different gravitational fields. These were not decorative mysteries. They were measurements, and they turned the geometry of space-time into physical science. Once gravity becomes geometry, the next question is unavoidable. If space can curve, can time curve too? If a clock sits near Earth and another sits higher above it, do they keep identical time? The answer is one of the strangest and most practical facts in modern physics. Gravity does not only shape where things go, it also changes how time passes. Imagine two perfect clocks. One is placed near sea level. The other is carried to the top of a mountain. They are built the same way, set with the same care, and protected from ordinary disturbance. If you waited long enough and compared them with enough precision, they would not agree perfectly. The higher clock would tick slightly faster than the lower one. Can gravity change time? In general relativity, yes. A clock deeper in a gravitational field ticks more slowly compared with a similar clock higher up. Near Earth, the difference is tiny, but it is real and measurable. Time is not a universal river flowing at exactly the same rate everywhere. It is part of space-time, and space-time is affected by mass and energy. This does not mean the lower clock feels broken. Locally, each clock behaves normally. If you were beside either one, seconds would pass in the ordinary way. The difference appears when the clocks are compared from different positions in a gravitational field. Time dilation is not a feeling in the clock. It is a relationship between clocks following different paths through space-time. Here is the surprising part. This effect matters to technology in your pocket. GPS satellites carry precise clocks, and those clocks do not tick exactly like clocks on Earth's surface. They are moving relative to the ground, which brings in special relativity, and they are higher in Earth's gravitational field, which brings in general relativity. Without corrections, navigation errors would build up quickly. A phone locating you on a road quietly depends on the fact that time runs differently in orbit. The idea is almost unsettling because we are used to thinking of time as the background against which events happen. Relativity changes that. Time is not merely a universal clock on the wall of the universe. It is woven into the same structure as space. Gravity affects that structure, so gravity affects time. The difference may be tiny near Earth, but the principle is enormous. If you could move closer to a very massive compact object, the effect would become more dramatic. Far from a black hole, a clock could tick almost normally compared with distant clocks. Near the event horizon, as seen by a faraway observer, time would appear deeply slowed. We do not need to make black holes the center of this gravity story, but they show the principle in its strongest familiar form. Strong gravity can make time behave in ways ordinary life never prepares us for. Even near Earth, the principle has a philosophical edge. Two people at different heights are not aging at exactly the same rate, though the difference is tiny. A person on a mountaintop, a person at sea level, and a satellite clock are all tracing slightly different histories through space-time. The effect does not disturb daily life because it is so small, but the measurement says something profound. Time is local enough to be influenced by where you are in a gravitational field. Near Earth, the effect is subtle enough that only precision reveals it. Modern atomic clocks are so accurate that differences in height can matter. A clock slightly higher in a gravitational field ticks at a measurably different rate from one lower down. The mountain and sea level picture is not fantasy. It is a real feature of the world, hidden by the coarseness of ordinary experience. This also changes the meaning of now. Across everyday distances, we can pretend there is one universal present. The approximation works because the effects are small. But at high speeds, strong gravity, or great distances, simultaneity and clock rates become more complicated. The universe does not keep time with a single central metronome. Each path through space-time has its own proper time. From the viewpoint of your own body, this is quiet but profound. Standing on Earth, you are lower in the planet's gravitational field than a satellite above you. Your clock, your cells, and your thoughts belong to a slightly different gravitational time than a clock in orbit. The difference is far too small to feel, but not too small for physics to measure. Once gravity can change time, it should no longer surprise us that it can also change the path of light. Light has no rest mass, yet it travels through space-time. If space-time is curved, then even light must follow that curvature. The next scene begins not with a clock, but with a distant galaxy whose image has been stretched into an arc by invisible mass. Imagine looking through a powerful telescope at a massive cluster of galaxies. In the foreground are hundreds or thousands of galaxies bound together by gravity. But behind them, much farther away, are other galaxies whose light has traveled for billions of years. Instead of appearing as simple points or small ovals, some of those background galaxies look stretched into arcs, smeared into curves, or multiplied into several images around the cluster. How can gravity bend light? Light has no rest mass, so the old idea of gravity simply pulling on massive objects is not enough. In general relativity, light follows the geometry of space-time. When a massive object curves that geometry, the path of light curves with it. The light is not being grabbed like a rope. It is taking the straightest available route through a curved space-time. This effect is called gravitational lensing. A galaxy cluster can act like a natural telescope, bending and focusing light from objects behind it. The cluster does not need to be transparent like glass. It lenses because mass changes geometry. Stars, gas, galaxies, and dark matter all contribute to the total curvature, and the path of light responds to the combined mass along the line of sight. Here is the surprising part. Lensing can reveal mass that does not shine. Astronomers can study the distorted images of background galaxies and infer how much mass must be present in the foreground cluster. If the visible galaxies and hot gas do not provide enough mass to explain the bending, something unseen must be contributing. This is one of the ways dark matter enters the story, not as a decorative mystery, but as an inference from motion, light, and gravity. If you could hover near the path of one of those light beams, nothing would feel bent locally. The light always moves at light speed through its local space. But across cosmic distances, tiny changes in direction accumulate. By the time the light reaches Earth, the image can be warped into an arc. The telescope receives not only light from a galaxy, but evidence about the gravitational landscape the light crossed on its way. A familiar lens, like a magnifying glass, works because material bends light through refraction. A gravitational lens works because space-time itself changes the path. The comparison helps, but the mechanism is different. There is no glass between the galaxies. There is mass, geometry, and the long patience of light traveling through a universe that is not perfectly flat. Some lenses are strong enough to make spectacular arcs and multiple images. Others are subtler, producing tiny statistical distortions in the shapes of many background galaxies. Astronomers can analyze those small distortions together and build maps of mass across large regions of sky. The effect may be too slight for one image to announce itself, but across thousands of galaxies, the pattern becomes evidence. Gravity can write faintly and still be read. This makes lensing one of the most elegant tools in astronomy. It can magnify distant galaxies that would otherwise be too faint to study. It can map the mass of clusters. It can reveal dark matter distributions. It can even produce multiple images of the same object, with light taking different routes around a foreground mass and arriving at different times. The sky becomes a set of clues, and gravity becomes the investigator's map. The quiet correction is that seeing is not always straightforward. A telescope does not simply show us where things are in a naive sense. It shows light after that light has traveled through curved space-time. Around massive structures, the apparent position, shape, and brightness of an object may all be altered. The universe is visible, but it is not visually simple. From here, the gravity story widens. If light can reveal invisible mass, then the motions of stars can do the same. When astronomers looked carefully at galaxies, they found stars moving too fast for the visible matter alone. The next chapter begins inside a spiral galaxy, where the outer stars seem to know about a mass we cannot directly see. Imagine you are looking down on a spiral galaxy from far above its disk. The center glows with old stars. The arms curl outward in pale blue and gold, traced by gas clouds, dust lanes, and regions where young stars are forming. It looks almost like a wheel, but it is not a solid wheel. It is a gravitational system made of hundreds of billions of stars, clouds of gas, dark dust, and a much larger invisible halo whose presence is known by motion. What would you expect the outer stars to do? If most of the mass were concentrated in the bright center, then stars farther out should move more slowly, much as planets farther from the sun orbit more slowly than inner planets. In the solar system, the sun holds most of the mass, so distance strongly changes orbital speed. A galaxy looks at first as if it might follow a similar pattern, with the bright central regions doing most of the gravitational work. But many galaxies do not behave that way. Stars far from the center often move faster than expected from visible matter alone. Their rotation curves stay flatter than simple visible mass models predict. The outer stars move as if there is more gravitational mass present than telescopes can see in stars, gas, and dust. This is one of the major lines of evidence for dark matter. The phrase can sound like a label for ignorance, but it is more precise than that. Dark matter is matter inferred from gravitational effects that does not emit, absorb, or reflect light in the ordinary ways telescopes detect. Its particle nature remains unknown, but its gravitational influence appears in galaxy rotation, galaxy clusters, lensing maps, and the large-scale structure of the universe. The important habit here is restraint. Scientists do not say dark matter exists because the galaxy looks mysterious. They say visible matter does not provide enough gravity to explain several independent observations under standard physics. The outer stars are one clue. Lensing is another. Cluster behavior is another. The cosmic web is another. Each clue has its own details and uncertainties, but together they point toward a missing mass component that behaves gravitationally. If you could ride with an outer star in a spiral galaxy, the motion would not feel unusual locally. The star follows a path shaped by the total gravitational field around it. But when astronomers map many stars and gas clouds across the disk, the pattern tells a larger story. The visible galaxy is not the whole gravitational system. It appears to sit inside a broad halo of unseen mass. A useful comparison is traffic at night. If you saw headlights moving along curves in darkness, you could infer roads even before the road surface became visible. In galaxies, the moving stars and gas are the headlights. Their speeds reveal the gravitational road. The invisible halo is not seen directly, but the motion points to it. This correction matters because galaxies are not simply luminous islands. The bright disk is only part of the structure. A galaxy includes dark matter, gas reservoirs, stellar halos, central regions, magnetic fields, and often a central black hole, though the black hole is usually not what controls the motion of the outer disk. The galaxy is a layered gravitational ecosystem, not just the bright spiral in a photograph. Here, gravity becomes a detective tool. It tells us that the universe contains more than it shows in light. The stars move, and their motion refuses to match the visible mass. The refusal is not an embarrassment. It is evidence. Science often advances when nature does not fit the first picture, and the mismatch becomes too consistent to ignore. From one galaxy, the view now widens to many. If galaxies are gravitational systems, then clusters are systems of systems, cities of galaxies, hot gas and dark matter, all bound together on scales so large that light itself becomes a measuring tool. Imagine approaching a galaxy cluster. At first, it may look like a field of scattered lights, as if many galaxies simply happen to lie in the same direction. But a true cluster is not a chance alignment. It is a gravitationally bound system containing hundreds or thousands of galaxies, vast clouds of hot gas, and a dominant mass component that cannot be seen directly in ordinary light. What holds a cluster together? The visible galaxies contribute mass, but they are not enough. Between them is extremely hot gas, detectable in X-rays, spread through the cluster like a thin, glowing atmosphere. This gas can contain more ordinary matter than the stars and the galaxies themselves. Yet even stars and gas together still do not account for the total gravitational mass inferred from cluster dynamics and lensing. Galaxy clusters show dark matter on some of the largest bound scales in the universe. The galaxies move too quickly to be held by visible matter alone. The hot gas sits in a gravitational well deeper than the visible material can explain. Background galaxies appear distorted by lensing, and the bending requires a larger mass distribution than luminous matter provides. Three different kinds of evidence point toward the same hidden weight. If a galaxy is like a city of stars, a cluster is more like a continent of cities. But the comparison has limits. The cluster is not solid. The galaxies are separated by immense distances. Most of the volume is thin gas and empty-looking space. Gravity is the structure that makes it one system. Without that shared gravitational field, the galaxies would not belong to the same cosmic city. Here is the surprising part. Much of the ordinary matter in clusters is not in stars. It is in hot, diffuse gas spread between galaxies. This gas can reach temperatures so high that it shines in X-rays rather than visible light. To human eyes, the cluster may look mostly like separate galaxies. To X-ray telescopes, it becomes a glowing reservoir of plasma. To gravitational lensing, it becomes a map of total mass. Each observational method gives a different layer. Optical telescopes show stars and galaxies. X-ray observatories reveal hot gas. Lensing reveals mass regardless of whether it shines. When these layers are compared, the cluster becomes a kind of cosmic laboratory for gravity. It lets scientists test how visible matter, dark matter, and space-time curvature align. In some cluster observations, these layers do not sit in exactly the same place, and that separation can be scientifically powerful. Hot gas can be slowed by collisions and pressure, while dark matter, if it interacts mostly through gravity, can pass through more easily. When astronomers compare the gas, galaxies, and lensing mass, they are not only weighing a cluster, they are asking what kinds of matter respond to collision, pressure, and gravity in different ways. This is where gravity's weakness becomes almost difficult to believe. The force that could barely move two laboratory objects toward each other becomes, across millions of light years, the binding principle of entire galaxy clusters. It gathers not by strength at a point, but by persistence over scale. Matter keeps responding, and over cosmic time the response becomes architecture. From inside such a cluster, the sky would be crowded by galactic neighbors, yet each neighbor would still be unimaginably far away. Space remains vast, even inside one of the densest large structures in the universe. The quiet lesson is that gravity does not make the cosmos small. It gives the vastness a pattern. And beyond clusters lies an even larger pattern. Pull back far enough, and galaxies no longer appear as isolated islands. They arrange along immense filaments, leaving great voids between them. The next view is not a galaxy or a cluster, but the cosmic web itself. The large-scale structure gravity grew from tiny early differences. Imagine pulling back until individual galaxies become points of light. Then pull back farther until even clusters become knots in a larger pattern. The universe no longer looks evenly sprinkled. It begins to resemble a web, long filaments of galaxies stretching across space, dense nodes where clusters gather, and enormous voids where comparatively little matter resides. How did the universe become web-like? The answer begins with tiny differences in density in the early cosmos. The young universe was almost smooth, but not perfectly smooth. Some regions were very slightly denser than others. Gravity amplified those differences. A slightly denser region pulled in more matter, becoming denser still, while less dense regions became emptier by comparison. Over billions of years, small initial variations grew into the large-scale structure we see today. This is one of gravity's most important habits. It turns small imbalances into larger ones. If a region has a little more matter, it has a little more gravitational pull. That extra pull draws in more material. The process is slow, but the universe has had a long time to work. The filaments and clusters are not random decorations. They are the historical record of gravitational growth. Dark matter plays a central role in this story. Because it does not interact with light the way ordinary matter does, it could begin clumping gravitationally while ordinary matter was still strongly coupled to radiation in the early universe. Later, ordinary matter fell into the gravitational scaffolding shaped largely by dark matter. Stars and galaxies lit up along a structure whose invisible framework was already forming. This means the cosmic web is not only a present-day map, It is a history of growth. The pattern carries information about the early universe, the amount of matter present, the behavior of dark matter, and the influence of dark energy on expansion. Large surveys that map millions of galaxies are not just making beautiful pictures. They are measuring the statistical arrangement of matter to test the story of how structure formed. If you could see both ordinary matter and dark matter at once, the cosmic web would look less like a pattern painted by starlight and more like a deep gravitational landscape. The bright galaxies trace the densest regions, but the full structure includes mass that does not shine. Light reveals the visible population. Gravity reveals the underlying arrangement. The voids are just as meaningful as the filaments. They are not empty in an absolute sense, but they contain far fewer galaxies than the denser regions. Matter flowed away from underdense regions and into denser ones, making the contrast stronger over time. The universe became textured. It developed geography on scales so large that ordinary maps lose their intuition. Here is the quiet correction. The cosmic web is not a solid net stretched through space. It is a statistical gravitational structure made of moving galaxies, gas, dark matter, and expanding space-time. The filaments are not cables. The nodes are not fixed anchors. Everything is evolving, orbiting, merging, and separating within the larger history of cosmic expansion. The beauty of the web is that it shows gravity as memory. It remembers the early density pattern by amplifying it. It turns minute beginnings into observable structure. The largest shapes in the universe began as tiny differences, strengthened not by forceful drama, but by persistent attraction over cosmic time. But this raises the next question. If gravity pulls matter together, why does the universe expand at all? Why are distant galaxies receding while local systems remain bound? To understand that, we need to hold two truths at once. Gravity gathers matter locally, while space itself expands on the largest scales. Imagine standing in your room and asking whether the space around you is expanding. The universe is expanding, so should the walls slowly move apart? Should Earth grow larger? Should the solar system stretch? The answer is no. Your room is held together by electromagnetic forces in matter. Earth is held together by gravity and material strength. The solar system is gravitationally bound. Cosmic expansion becomes important across enormous distances, not inside systems that are already bound. How can gravity pull things together while the universe expands? The key is scale. Locally, gravity can overcome expansion and bind structures such as planets, stars, galaxies, and galaxy clusters. On larger scales, where matter is spread more thinly and systems are not bound together, the expansion of the universe becomes visible as distant galaxies recede from one another. This means cosmic expansion is not like ordinary objects flying through pre-existing space after an explosion. It is better understood as the large-scale increase of distances in space-time itself. Galaxies that are not gravitationally bound to us are carried into greater separation as the universe evolves. They are not necessarily racing through space like fragments from a blast. The space between distant systems is changing. Here is the useful correction. Expansion does not tear apart your body, your house, Earth, or the Milky Way. Bound systems remain bound because local forces dominate. The Andromeda Galaxy, for example, is moving toward the Milky Way under mutual gravity despite the overall expansion of the universe. Cosmic expansion is real, but it does not act like a stretching rubber sheet on every small structure equally. At the same time, gravity does not control the whole cosmic future by itself. Observations show that the expansion of the universe is accelerating. The name dark energy is given to whatever is driving that acceleration in current cosmological models. It is not a familiar substance in the everyday sense. It is a label for a real observed effect whose physical nature remains one of the major open questions in cosmology. The discovery of acceleration changed the emotional shape of cosmology. For a long time, one natural question was whether gravity would eventually slow expansion enough to halt it or reverse it. The evidence for acceleration showed that the story was not that simple. Something in the model behaves as if it has negative pressure, changing the expansion history. The name dark energy is useful, but it should not fool us into thinking the underlying physics is fully understood. If you could watch the universe on the largest scale, you would see two tendencies in tension. Matter gathers into galaxies, clusters, and filaments through gravity. Meanwhile, the average separation between distant unbound regions increases. The universe is not simply collapsing under attraction, and it is not simply flying apart without structure. It is doing both in different regimes. This is why the cosmic web can exist in an expanding universe. Gravity gathered matter where density was high enough, forming local and regional structures. Expansion continued across the wider space-time background. Bound islands formed in a stretching sea. The comparison is imperfect, but the principle is clear. Local binding and cosmic expansion can coexist. The surprising part is that your everyday stability is connected to this larger distinction. Your room is not expanding because forces within matter are enormously effective on that scale. Earth is not expanding because its gravity and internal structure hold it together. The galaxy is not expanding because its stars are bound within a shared gravitational system. Expansion becomes visible only when the distances are immense and the binding is too weak to overcome the large-scale evolution of space. At the edge of this idea, gravity becomes both powerful and limited. It builds structure, but it may not decide the final fate of the universe alone. Dark energy, whatever it truly is, changes the cosmic story. And so gravity's role becomes more interesting, not less. It is the great gatherer inside a universe whose largest scale behavior is still under investigation. From here, we can move from the universe's largest structures to one of gravity's most creative acts. In cold clouds of gas and dust, far from any human eye, gravity begins gathering material until a star is born. Imagine entering a cold molecular cloud, a dark region of gas and dust spread across light years. To the eye, it might look almost empty, but it contains the raw material of future stars. Hydrogen molecules drift. Dust grains absorb and scatter light. Magnetic fields thread the cloud. Turbulence stirs it. And within the cloud, some regions are slightly denser than others. How does gravity make a star? It begins when a region becomes dense and cool enough for its own gravity to overcome the support of gas pressure, turbulence, magnetic effects, and surrounding motions. The material starts to contract. As it falls inward, the cloud can fragment into smaller clumps. Each clump gathers more matter, becoming a protostar wrapped in a rotating disk. Gravity is the engine of collapse, but not the only actor. Gas pressure resists compression. Magnetic fields can channel and slow motion. Turbulence can both support the cloud and create dense pockets where collapse begins. Radiation from young stars can heat and push surrounding gas. Star formation is not simply gravity winning in one clean step. It is a negotiation among forces, with gravity deciding the direction of the long-term gathering. As material falls inward, gravitational energy becomes heat. The forming center grows hotter and denser. At first, it is not yet a true star. It is a protostar, shining partly because infalling material releases energy. Only when the core becomes hot and dense enough can hydrogen fusion begin. Then, the object enters the long, stable phase of stellar life, balancing inward gravity against outward pressure produced by fusion energy. Rotation also becomes important during collapse. A large cloud may begin with only a slight overall spin, but as material contracts, conservation of angular momentum makes the rotation more noticeable, much like a skater spinning faster when drawing in their arms. The material cannot all fall straight into the center. Some of it settles into a disk, and that disk becomes the place where jets can launch and where planets may later form. Here is the surprising part. A star is born from gravity, trying to make matter fall inward, but the star lives because that inward pull is resisted. The sun exists as a balance. Gravity compresses it. Fusion in the core creates pressure that pushes outward. For billions of years, those tendencies can remain in steady opposition. A star is not a fire in the ordinary sense. It is a gravitationally confined fusion reactor. If you could watch the process sped up, the cloud would not collapse neatly into one glowing ball. It would form knots, disks, jets, cavities, and clusters. Young stars often appear in groups because large clouds fragment. Some material is gathered into stars. Some remains in disks. Some is blown away by radiation and outflows. Gravity begins the gathering, but feedback from newborn stars changes the environment that made them. A familiar comparison is a snowball rolling downhill, collecting more snow as it goes, but the comparison only goes so far. A forming star is not rolling through a solid landscape. It is drawing gas inward from all directions, heating as it contracts, spinning faster as material falls into a disk, and eventually igniting fusion in its core. The physics includes motion, energy, pressure, radiation, magnetism, and chemistry. From the outside, a star-forming region can look like a dark cloud hiding light. From within, it is a slow transformation of scattered matter into luminous structure. Gravity takes what is cold and diffuse and gathers it toward a center where temperature and pressure rise. The result is not only a star, but a new source of light, heat, elements, and future worlds. And around many young stars, the leftover material does not vanish immediately. It settles into a rotating disk of gas and dust. Inside that disk, gravity continues its patient work, organizing rings, clumps, and collisions until planets may begin to grow. Imagine standing safely inside a young star system, looking across a vast rotating disk. The newborn star glows at the center, surrounded by gas and dust arranged in broad rings and gaps. Tiny grains drift through the disk. Larger particles collide, stick, break apart, and gather again. The scene is not a finished solar system. It is a construction zone where gravity is beginning to turn leftovers into worlds. How does loose dust become a planet? The answer is still an active area of research, but the broad picture begins with disks around young stars. As a cloud collapses, rotation becomes important. Material with angular momentum does not fall straight into the star. It spreads into a disk, and within that disk, dust grains can grow through collisions, gas drag, concentration and pressure traps, and gravitational gathering. Gravity is essential, but it does not act alone. At the smallest sizes, electrical and surface forces can help grains stick. Gas drag changes how particles move. Turbulence can concentrate or scatter solids. Once bodies grow large enough, their own gravity helps them attract more material. Planetesimals can collide and merge into planetary embryos. In some regions, gas giants may gather massive atmospheres before the disk disperses. Here is the surprising correction. Planet formation is not just dust slowly clumping like lint under a bed. The disk is dynamic. It has temperature gradients, chemical zones, magnetic effects, pressure structures, and migrating bodies. Young planets can carve gaps. Rings can appear before planets are fully formed. Collisions can build worlds or shatter them. The process is both constructive and violent. If you could shrink the solar system's early disk into something room-sized, the dust would not look packed solid. It would be extraordinarily thin by human standards. Planet formation happens in a disk that is huge, sparse, and long-lived enough for countless interactions. Gravity does not need density to look like a wall. It needs time, motion, and repeated encounters. The planets that form remember where they were born. Near a young star, heat keeps many volatile materials from condensing, favoring rocky worlds. Farther out, colder regions allow ices to become part of growing bodies, providing more solid material and changing the pathways toward giant planets. The architecture of a planetary system is therefore partly a map of temperature, chemistry, gravity, and time. Modern telescopes have made this story visible in a new way. Observations of protoplanetary disks show rings, gaps, spirals, and asymmetries around young stars. These images are not photographs of finished planets in every case, but they reveal the environments where planets form. The disk itself becomes evidence that gravity is organizing matter long before a world has a clear surface. The rings and gaps are especially useful because they invite careful interpretation. A gap may suggest a forming planet, but other disk processes can also create structure. Scientists compare images with simulations, chemistry, dust size, gas motion, and temperature to decide what is likely. The point is not to force every ring into a planet story. The point is that planet formation leaves traces, and gravity helps translate those traces into testable models. A planet is not simply a rock that became large. It is the outcome of many processes: dust sticking, bodies colliding, orbits changing, gas flowing, and gravity amplifying small advantages. A world grows because matter finds ways to meet, lose energy, and remain bound. The quiet phrase planet formation contains millions of impacts and countless orbital adjustments. From within the disk, gravity is not only pulling inward toward the star, it is also binding particles to each other, shaping orbital lanes, helping clumps survive, and sometimes driving collisions that reset the work. The result can be a system of rocky planets, gas giants, icy bodies, moons, rings, and debris. A star forms from collapse. A planetary system forms from what keeps moving around it. But gravity does not only build. In extreme conditions, it can also compress, strip, tear, and reshape. To understand that side without returning fully to the previous black hole topic, we look briefly at extreme gravity as a correction. Not magic suction, but mass, distance, curvature, and tidal force. Imagine approaching the idea of a black hole from a safe distance, not as a monster, not as a drain in space, but as a compact object whose mass has been packed into a region so small that space-time around it becomes extreme. From far enough away, its gravity is not magical. It behaves according to mass and distance, just as gravity does elsewhere. Does extreme gravity mean everything nearby is sucked in? No. This is one of the most important corrections. A black hole is not a cosmic vacuum cleaner. If the sun could somehow be replaced by a black hole of the same mass, Earth's orbit would not suddenly collapse inward because of stronger distant gravity. The sunlight would vanish, and life would face catastrophe for other reasons, but the gravitational pull at Earth's distance would be nearly the same. What makes a black hole extreme is compactness. The mass is confined within such a small region that close to it, space-time curvature becomes severe. Paths that would lead outward farther away can fail near the event horizon. Light can still move at light speed locally, but inside the horizon, all future-directed paths lead inward. The danger is not a special sucking power. The danger is what the geometry becomes when mass is concentrated enough. Tidal forces are another part of the story. Because gravity changes with distance, the side of an object closer to a compact mass can be pulled much more strongly than the far side. This difference can stretch and compress matter. Near a small black hole, tidal forces close to the horizon could be destructive. Near a supermassive black hole, the gradient at the horizon can be much gentler, though deeper inside the outcome remains unavoidable. Here is the quiet correction. The event horizon is not a material surface. You could not touch it like a wall. It is a boundary in space-time, defined by whether signals can escape to the outside universe. The black hole itself does not need a glowing edge. Its presence is revealed by orbits, accretion disks, jets, lensing, and gravitational waves from mergers. The word singularity also needs care. In classical general relativity, some black hole solutions contain singularities where density and curvature become infinite in the equations. But this does not mean astronomers have photographed a singularity or that we possess a complete physical description of the center. A singularity is a sign that the known theory has reached a limit. It tells us the map is unfinished. This is where black holes are useful for the wider gravity story. They separate what is measured from what is inferred and what is unknown. We can measure orbits around compact masses. We can image shadow structures produced by light near horizons. We can detect waves from mergers. But the deepest interior is not observable in the same way. The lesson is not to make the mystery louder. It is to keep each layer in its proper place. From a safe distance, then, a black hole is both ordinary and extraordinary. Ordinary because gravity still depends on mass and distance. Extraordinary because close in, the curvature of space-time changes the future paths available to matter and light. It is not a break from physics. It is physics followed into a regime where ordinary intuition stops being reliable. This is why black holes belong in a gravity documentary, but not as the whole story. They are one extreme example of what gravity can do when mass becomes compact. They correct our myths and sharpen our understanding. Gravity is not always gentle, but even in its most dramatic forms, it is not magic. It is geometry, motion, energy, and evidence. And when extreme masses move violently, they can do something even stranger. They can send ripples through space-time itself. These ripples travel outward across the universe, carrying information not as light, but as changing distance. The next chapter begins with two massive objects spiraling together far away. Imagine two massive objects orbiting each other far beyond the Milky Way. They may be black holes, neutron stars, or other compact remnants. At first, their orbit is wide enough to seem almost steady. But with every circuit, energy leaves the system in a form that carries no light and makes no sound in air. The distance between them slowly shrinks. They spiral inward, faster and faster, until the final moments release a pulse through space-time itself. What is a gravitational wave? It is a ripple in space-time produced by accelerating masses, especially systems where enormous masses move in changing asymmetric ways. It is not a sound wave traveling through air. It is not a shock wave moving through gas. It is a change in the geometry of distance itself, spreading outward at the speed of light. If a gravitational wave passes through a region, it can stretch space slightly in one direction while squeezing it in another, then reverse the pattern. The effect is incredibly small by the time it reaches Earth from distant cosmic events. But small does not mean imaginary. The wave changes the relative distances between objects, and with precise enough instruments, that change can be measured. Here is the surprising part. Gravitational waves were predicted by general relativity long before they were directly detected. The theory said that space-time could carry disturbances, just as electromagnetic fields carry light. But gravity is weak, and the changes produced at Earth are minute. For decades, the challenge was not only believing the waves existed, but building an instrument delicate enough to notice them. A useful comparison is a message traveling not through a medium, but through the measuring ruler itself. If sound moves by compressing air, a gravitational wave moves by changing space-time distances. There is no air required. The wave can cross deep space, passing through stars, dust, planets, and galaxies with very little interruption, carrying news of motion that ordinary telescopes might not see. The strongest detectable sources are not gentle systems like Earth orbiting the Sun. They are extreme accelerations, compact objects spiraling together, merging and settling into new forms. In these events, gravity is not merely a background pull. It becomes dynamic. The shape of space-time changes violently enough to send a signal across cosmic distances. The reason compact objects are so important is that they can orbit very close together at enormous speeds. Ordinary stars can also produce gravitational waves in principle, but their motions are usually too smooth or too weakly asymmetric to create detectable signals at Earth. Dense remnants allow gravity to become concentrated, fast, and changing. The wave carries away orbital energy, and that energy loss helps drive the final inward spiral. This gives astronomy a new sense. For centuries, humans studied the universe mainly through light, visible light first, then radio, infrared, ultraviolet, X-rays, and gamma rays. Gravitational waves are different. They are not another color of light. They are space-time arriving as information. They tell us how massive objects moved, how compact bodies merged, and whether general relativity continues to hold under extreme conditions. From your imagined position far from the merger, you would not hear a boom. Space itself would carry the disturbance outward. By the time the ripple reached Earth, it would be almost unimaginably faint, but still patterned. Inside that pattern is the history of the orbit, slow at first, then rising in frequency and strength as the objects spiral inward. A waveform becomes a fossil of motion. The quiet wonder is that the universe can speak this way. Not with light from a surface, not with particles arriving from a source, but with the stretching and squeezing of distance. To receive such a signal, Earth needed a new kind of instrument, a ruler so precise it could notice changes far smaller than an atom across kilometers of length. Imagine standing beside one long arm of a gravitational wave detector. It stretches for kilometers, straight and quiet, with laser light traveling inside vacuum tubes. The instrument does not look like a telescope pointed at the sky. It looks more like a precise question built on the ground. Can Earth measure a passing ripple in space-time? How can a detector sense something so small? LIGO and similar observatories use laser interferometry. Laser light is split and sent down two long perpendicular arms. The beams reflect from mirrors and return. If the arm lengths change relative to each other, even by an incredibly tiny amount, the returning light produces a different interference pattern. A passing gravitational wave can create exactly that kind of relative change. The difficulty is almost hard to hold in the mind. The signal from a distant merger changes the arm lengths by a fraction far smaller than the width of an atom. The detector must distinguish that effect from vibrations, thermal noise, seismic motion, passing vehicles, wind, and countless other disturbances. It is not enough to build a long ruler. The ruler must be quiet, isolated, calibrated, and understood with extraordinary care. Here is the historic moment. On September 14th, 2015, LIGO made the first direct detection of gravitational waves. The event, called GW150914, came from a binary black hole merger. It confirmed a major prediction of general relativity and opened the era of gravitational wave astronomy. Earth had become, in a new sense, an instrument for feeling space-time. The detection was not a single machine saying yes in isolation. Multiple detectors helped confirm a signal and rule out local noise. The timing differences between observatories also help locate the source region on the sky. When the same pattern appears in separated detectors with the right delay, the evidence becomes much stronger. Gravity's whisper must survive the discipline of measurement. Before direct detection, there was already indirect evidence. Binary pulsars, pairs of dense stellar remnants with precisely timed signals, showed orbital decay consistent with energy being lost through gravitational waves. In those systems, astronomers did not catch the wave itself. They watched the orbit change in the way general relativity predicted. It was like seeing ripples leave a pond by watching two floating leaves slowly draw closer. That history matters because it shows how scientific confidence can build in stages. First, a theory predicts an effect. Then, indirect observations reveal consequences that match the prediction. Then direct instruments become sensitive enough to catch the effect itself. Gravitational wave astronomy did not appear from nowhere in 2015. It arrived after decades of theory, engineering, pulsar timing, detector development, and patient refusal to confuse hope with measurement. The direct measurement changed the field. It allowed scientists to study black hole mergers, neutron-star mergers, and compact object populations in a way light alone could not. A waveform reveals masses, spins, distances, and the dynamics of the final in spiral and merger. The shape of the signal becomes a test of the theory that predicted it. This is one of the deepest examples of patience in science. Einstein's equations described a possibility. Astronomers found indirect signs. Engineers and physicists built instruments of almost unreasonable precision. Then, a century after the theory was formed, a signal crossed Earth and was recognized. The universe did not become stranger that day. We became able to measure one more part of its strangeness. But gravitational waves do not always arrive alone. Sometimes the same cosmic event can speak in space-time and in light. When two neutron stars merged in 2017, detectors heard the wave, and telescopes saw the glow. One event reached Earth in two languages. Imagine two neutron stars orbiting each other. Each is the collapsed core of a once massive star, packed into a sphere only about the size of a city, though the exact properties depend on the star and the equation of state of dense matter. They circle faster and faster, losing energy through gravitational waves. In the final moments, space-time carries the first message outward. What can we learn when gravity and light arrive from the same event? The event known as GW170817 showed the power of multi-messenger astronomy. Gravitational wave detectors registered the signal from a neutron star merger, and telescopes later observed light from the same cosmic collision. The universe provided both a space-time waveform and electromagnetic radiation from matter involved in the event. The two messages carry different information. Gravitational waves reveal the motion of the massive compact objects, their in-spiral, their masses, and aspects of the merger dynamics. Light reveals matter, heated ejecta, radioactive decay, surrounding environment, and the host galaxy context. One messenger tells us how space-time was disturbed. The other tells us how material responded. Here is the surprising part. No single kind of observation owns the whole truth. Light can show glowing matter but may miss dark, compact motion. Gravitational waves can show the dance of dense objects even when little light escapes. Neutrinos, cosmic rays, and other messengers add still more possibilities. Modern astronomy is becoming less like looking through one window and more like listening to a system with several instruments at once. In a neutron-star merger, matter can be thrown outward under extreme conditions. These events are connected to the formation of heavy elements in current astrophysical understanding, though the exact contributions of different sites remain an active research topic. The important point for this gravity journey is that gravity did not merely pull objects together. It created a collision that became a laboratory for nuclear physics, radiation, and cosmic chemistry. If you could watch from a safe, impossible distance, the scene would unfold in stages. First, the orbital motion tightens. Then the gravitational wave signal rises. The merger occurs. Matter heats, ejects, and glows. Telescopes around Earth turn toward the source region, searching for changing light. A single event becomes a coordinated scientific response across the planet. The timing is scientifically valuable. Gravitational waves from the merger and light from the aftermath do not describe the same part of the event in the same way. The wave comes from the bulk motion of dense masses. The light comes from matter interacting, heating, expanding, and radiating. Comparing them can test how fast gravitational waves travel, help estimate cosmic distances, and connect compact object physics to observable light. This is a correction to the idea that gravity is only a silent background. In extreme systems, gravity can announce itself. It can set the timing of a merger, shape the motion of dense matter, produce waves in spacetime, and help create conditions where light later emerges. Gravity and radiation become different chapters of the same event. The phrase, "one event in two languages," matters because it shows how science builds a fuller picture. The gravitational wave signal is not a replacement for light, and light is not a replacement for the wave. Together, they let scientists ask better questions. How fast is the universe expanding? What happens to dense matter? How are heavy elements produced? And how well does relativity describe the signal? After seeing gravity as a cosmic messenger, we return to a more human question. Could people ever build the feeling of weight away from planets? If weight is a support force, and if acceleration can imitate gravity, perhaps the experience of standing can be engineered. The next chapter begins inside a rotating space habitat, where the floor seems to hold you for a very different reason. Imagine stepping onto the inner floor of a large rotating space habitat. The structure turns slowly around its central axis. Your feet press into the floor. A loose object placed beside you does not float aimlessly. It tends to move toward the floor with you. From inside, the sensation might resemble weight. But this is not because the habitat has created a planet's worth of mass. It is using motion to simulate gravity. What does artificial gravity usually mean? In realistic engineering discussions, it usually means simulated weight through acceleration or rotation, not the creation of a new gravitational field like Earth's. A rotating habitat can make occupants feel pressed toward the outer wall because the floor provides the inward force needed to keep them moving in a circle. Your body tends to move straight by inertia, while the rotating floor continually turns your path. The sensation comes from contact. The floor pushes on your feet. Your feet push on the floor. That support force travels through your body much like weight does on Earth. Locally, it can feel as if there is a down direction toward the floor, even though the cause is rotation rather than a massive planet beneath you. Here is the important trade-off. Radius and spin rate matter. A large habitat can rotate more slowly to produce the same felt acceleration as a smaller one spinning faster. Faster rotation can create stronger Coriolis effects, where moving your head or arms produces sideways sensations because different parts of your body are moving through the rotating frame. For this draft, we should avoid exact comfort thresholds unless the sources are upgraded, but the general trade-off is well established. If you stood in a small, fast-spinning room, turning your head might feel odd because your inner ear and body would detect rotation. In a much larger, slower-turning ring, the same level of simulated gravity could feel calmer. The comparison is like taking a curve in a compact spinning ride versus walking inside a vast wheel whose motion is gentle enough to fade into the background. This corrects a common science fiction shortcut. Artificial gravity is often shown as if a switch simply turns on a downward pull. Real physics gives us more constrained options. We can simulate weight through acceleration. We can rotate structures. But creating Earth-like gravity by assembling enough mass would require a planet-scale amount of matter, which is not a practical habitat design. Space stations today do not use large rotating living environments. Astronauts in microgravity rely on exercise, nutrition, medical monitoring, and operational countermeasures to reduce health effects. Rotating habitats remain serious concepts and experimental questions, not routine human homes already in operation. The image of a spinning space city is scientifically grounded, but still mostly belongs to future engineering. The engineering challenge is not only making a structure spin. A habitat would need stability, bearings, or structural designs that manage rotation, ways to dock vehicles, systems for moving between rotating and non-rotating sections, and human factors that keep daily life workable. Gravity can be simulated in principle by acceleration, but making that simulation comfortable, reliable, and safe over long periods is a much larger problem than drawing a wheel in space. From inside such a habitat, the feeling would return us to the opening chapter. Weight is not only gravity as a pull, it is the body experiencing support. On Earth, support comes from the ground resisting gravitational freefall. In a rotating ring, support comes from the floor redirecting your inertial motion in a circle. Different causes can produce similar sensations. And this leads to one of Einstein's most powerful insights. If acceleration can feel like gravity in a local setting, then perhaps gravity and acceleration are deeply related. To explore that, imagine a windowless room far from any planet, beginning to accelerate upward through empty space. Imagine you are inside a windowless room floating far from stars and planets. At first, you and every object inside drift freely. Then the room begins accelerating upward. The floor rises into your feet. A loose ball appears to fall toward the floor. Your body presses downward against the surface. Without windows, how would you know whether you were in a gravitational field or in an accelerating room? This is the heart of the equivalence principle. Locally, the effects of acceleration can resemble the effects of gravity. Standing in a windowless, accelerating spacecraft can feel like standing on a planet. The floor pushes upward on you, and your body interprets that support as weight. The ball that seemed weightless now meets the floor because the room accelerates into it. The principle does not say all gravitational situations and all accelerations are identical in every possible way. The word locally matters. In a small enough region, over a short enough time, the effects can be indistinguishable. But across larger regions, tidal effects can reveal differences. A real planet's gravity points toward its center, so two falling objects separated by distance may converge slightly. In a uniformly accelerating room, the geometry of the situation is different. Here is the surprising insight. Einstein used this kind of thought experiment to rethink gravity itself. If a person in free fall feels weightless, perhaps free fall is the natural state of motion. If a person standing on Earth feels weight, perhaps the ground is accelerating them away from that free fall path by pushing upward. The ordinary feeling of rest becomes, in relativistic terms, a kind of forced motion. This turns daily intuition inside out. You feel stationary when standing on Earth because the ground does not move beneath you in the ordinary sense. But physics says your body is being prevented from following a free-fall path through space-time. The support force is real. Your weight is the evidence. The ground is constantly pushing you away from the path you would take if nothing held you. A familiar elevator gives a smaller version of the idea. When an elevator accelerates upward, you feel heavier for a moment because the floor must push harder to accelerate your body. When it accelerates downward, you feel lighter because the support force is reduced. In a freely falling elevator, the support force can vanish and objects inside float. The sensation changes not because gravity disappears, but because support changes. If the elevator were large enough and the measurements precise enough, the difference between a real gravitational field and uniform acceleration could begin to show. Two objects dropped on opposite sides of the elevator near Earth would fall along paths that point very slightly toward Earth's center. That tiny convergence is a tidal clue. It tells you the field is not perfectly uniform. This is why the equivalence principle is local. It works in a small region before tidal differences become important. The equivalence principle became a doorway to general relativity. It suggested that gravity was not simply a force like others, but something connected to frames of reference, free fall, and the geometry of space-time. From that doorway came the idea that mass-energy curves, space-time, and free objects follow geodesics, the natural paths through that curved structure. From inside the windowless room, the lesson is deeply practical. Weight is not a simple label. It can be produced by a planet, simulated by rotation, increased or reduced by acceleration, and removed by freefall. Your body feels support force. Physics asks what path through space-time the body is being prevented from taking. To test such ideas, scientists need measurements of extraordinary subtlety. They do not merely ask whether gravity feels fair. They measure whether different objects fall the same way, whether g can be determined precisely, and whether tiny deviations might reveal something new. The next chapter enters the laboratory, where gravity is so weak between ordinary masses that the experiment must wait in stillness. Imagine a quiet laboratory instrument suspended so delicately that a tiny gravitational attraction between ordinary masses can twist it. There is no dramatic motion. No object leaps across the room. The signal is a slight turn, a minute displacement, a change so small that vibration, temperature, air movement, and nearby mass can interfere. To measure gravity between human-scale objects, science must become patient. Why is G so hard to measure? The gravitational constant describes the strength of gravity in Newton's law, but gravity between laboratory-sized masses is extremely weak. A person can feel Earth's pull because Earth is enormous. Two smaller masses in a lab attract each other far more faintly. Detecting that attraction requires isolating the experiment from environmental noise and knowing the geometry and mass distribution with great care. Henry Cavendish's famous torsion balance experiment measured the attraction between masses and allowed Earth's density, and later the gravitational constant in modern framing, to be inferred. The apparatus used a suspended rod with small masses and nearby larger masses. Their mutual gravity twisted the suspension slightly. The twist revealed a force far too small for the body to feel directly. Here is the surprising part. Even today, G remains one of the hardest fundamental constants to measure precisely. Different experiments can disagree by more than their stated uncertainties. The problem is not that gravity is unreliable in everyday motion. It is that the force between lab masses is so small and the measurement so sensitive to hidden effects that precision becomes extraordinarily difficult. This gives gravity a strange dual personality. It is obvious enough to make every object fall, yet elusive enough that measuring its constant in the laboratory remains challenging. You do not need delicate instruments to know that a drop stone accelerates downward. But to measure the tiny pull between two metal spheres, the room itself becomes part of the experiment. Scientists also test the equivalence principle with increasing precision. The question is whether different objects fall the same way in a gravitational field, independent of their composition, when other forces are controlled. This idea sits at the foundation of general relativity. Experiments on Earth and in space have tested it with remarkable sensitivity. The point is not to assume gravity's fairness, but to measure it. Sometimes apparent anomalies become ordinary physics after careful work. A famous example is the Pioneer anomaly, a small, unexpected acceleration once seen in spacecraft tracking. It is now widely explained by uneven thermal radiation from the spacecraft producing a tiny recoil effect. Heat leaving a machine in one direction more than another can mimic a mysterious force. The lesson is not that all anomalies are trivial. It is that nature asks for careful accounting. This kind of caution is especially important in gravity because the effects can be so small. A nearby hill, groundwater, building materials, temperature gradients, or a passing truck can matter to a sensitive experiment. When a measurement is trying to isolate a tiny gravitational signal, the world outside the apparatus becomes part of the calculation. Precision is not only a better instrument, it is a better understanding of everything that might imitate the effect. If you could watch the laboratory from outside, the scene would look almost still. But inside the data, tiny effects are being separated. Gravitational attraction, thermal drift, mechanical stress, seismic vibration, electromagnetic influence, and instrument noise. Measuring gravity means listening for one quiet voice in a room full of whispers. This is how physics protects wonder from exaggeration. It does not rush every unexplained signal into a new theory. It checks the instrument, the environment, the assumptions, and the analysis. Sometimes the result confirms the old rule more strongly. Sometimes it exposes a hidden ordinary effect. And sometimes, if the evidence is strong enough, it may point towards something new. The final chapter returns from the laboratory to the larger question. Gravity has carried us from the feeling of weight to galaxies, clocks, tides, waves, and precision tests. And still, at the deepest level, the map is not finished. Imagine returning to the place where the journey began. You are standing on Earth, feeling the surface beneath you. The room has not changed. The floor still supports your body. A dropped object would still fall. But now the feeling has a larger meaning. It is connected to orbit, tide, star formation, galaxy motion, lensing, time dilation, and waves crossing the universe. What do we still not know about gravity? We know an extraordinary amount. Newton's law works beautifully in ordinary and many astronomical settings. General relativity describes spacetime, predicts time dilation, explains light bending, and has passed demanding tests. Gravitational waves have been directly detected. Lensing maps reveal mass. Spacecraft navigation and GPS depend on gravitational physics. Gravity is not vague. It is one of the most precisely studied features of nature. And yet, the deepest map remains incomplete. General relativity describes gravity as the geometry of space-time. Quantum mechanics describes particles and fields at small scales with extraordinary success. But a complete experimentally confirmed theory that unifies gravity with quantum physics is still missing. At the overlap between the very massive and the very small, our best theories do not yet form one finished picture. This is why physicists speak of quantum gravity. The phrase does not name one settled theory. It names a problem: how to understand gravity when quantum effects cannot be ignored. Some approaches imagine strings, loops, causal structures, emergent spacetime, or other mathematical frameworks. These ideas are serious research programs, but no single approach has been confirmed as the final description of nature. Here is an important correction. Gravitational waves are not the same thing as gravitons. LIGO detects classical gravitational waves, ripples in spacetime. A graviton would be a hypothetical quantum particle of gravity in certain quantum frameworks. No individual graviton has been detected. The wave is measured. The quantum grain, if that language proves correct, remains beyond current evidence. Dark matter and dark energy also keep gravity's map open. Dark matter is inferred from gravitational effects in galaxies, clusters, lensing, and cosmic structure, but its particle nature remains unknown. Dark energy names the observed acceleration of cosmic expansion, but its physical identity is still uncertain. Some researchers explore modified gravity, asking whether gravity itself may need adjustment on cosmic scales. The mainstream framework remains dark matter and dark energy, but the questions are active. The boundary between established evidence and open interpretation is important. galaxy rotation curves, lensing, cluster mass, cosmic microwave background patterns, and large-scale structure are real observational pillars. Dark matter is the leading framework that explains them together, but the exact particle or particles have not been identified. Accelerated expansion is strongly supported by observations, but dark energy's nature remains uncertain. Gravity gives us the clues, and the universe has not yet handed over every answer. This is not a weakness of science. It is how science stays honest. A finished-looking story can be less truthful than an open map with careful labels. We know where the evidence is strong. We know where the equations work. We know where observations demand something unseen or unexplained. And we know where speculation must remain. Speculation until measurement catches up. From the human viewpoint, gravity is intimate. It shapes posture, balance, walking, falling, lifting, and the pressure of a chair beneath you. From the cosmic viewpoint, it gathers stars, organizes galaxies, bends light, slows clocks, and sends waves through spacetime. From the theoretical viewpoint, it points toward one of the great unfinished questions: what is spacetime at the deepest level? The quiet wonder is that all of these are the same subject. The feeling in your feet and the arc of a lensed galaxy are not separate stories. They are different scales of gravitational physics. A falling key, a rising tide, an orbiting moon, a rotating galaxy, and a passing gravitational wave all belong to one long chain of explanation. So, when you feel weight, you are not only feeling something ordinary, you are feeling the local form of a principle that reaches across the universe. Earth pulls. The ground answers. Your body is supported. And beyond that simple exchange, the same physics continues outward, shaping worlds, guiding light, testing time, and leaving some of the deepest questions still open. Gravity is familiar enough to hold the body and mysterious enough to keep physics unfinished. It is the everyday doorway into the largest structures and the smallest unknowns. The map is wide, and parts of it are still blank, but the path begins exactly where you are, on the surface of a planet, quietly held by a force you have known all your life.